So Hasan is my other brilliant student from Galatasaray University to talks about another side of Markov numbers. This is going to be for number theoretical sides, and it's going to be a story about rational approximations, which I think is very, very interesting. I was surprised that we were never taught this in school, like in university. Enjoy.
Thanks for the invitation. Hi. Thanks for the organization team. And it has been a pleasure to work with my mentor. Uh, We want to approximate real numbers by rational numbers. The construction of Cauchy sequences of real numbers says that every real number can be approximated by rational numbers. But we want to measure and we want to classify this approximation, how well can be made. The first is that every real number is in between two consecutive integers, Let's say this integer and so and satisfy this and alpha satisfy these inequalities. So alpha minus the absolute value of alpha minus n is smaller than 1. By the same reasoning, we can obtain for every natural number q, and we have the integer n with indexed by q, so this inequality holds. So the absolute value of alpha minus nq over q is smaller than 1 over q, because the length of the interval is 1 over q. Yes, can we do better? Yes. And Dirichlet's approximation theorem says for every alpha, I'm going to for every alpha and for every natural number n non-zero, we can find there exists a rational number p over q with q is smaller than n or equal. Then this inequality is satisfied. This is much general result than the preceding one. We are going to prove this theorem by the pigeonhole principle. As you can see in this terrible visualization, a reminder for pigeonhole principle. If this cardinality of the set of pigeons is greater than the cardinality of the set of pigeonholes, then there is no injective function from the set of pigeons to the set of pigeonholes. We are going to approximate this question with this observation. Let's take the interval from 0 to 1 and divide n equal interval and equal interval. So then consider these numbers. The fractional part of 1 times alpha, the fractional part of 2 times alpha, point. The fractional part of n plus 1 times alpha. And there is n plus 1 number. So two of them must lie in the same interval by the pigeonhole principle. Let's say those two integers are L and K. So we know L alpha and K alpha lie in the same interval. Say O(n) and E1 O(n). Then L alpha this means the fraction part of beta is beta minus the integer part of beta. Then the difference between L alpha minus K alpha is smaller than 1 over n, the absolute value, of course. And L minus K is smaller or equal than n, because we have and also n plus 1 number. So if we calculate this, L times alpha minus the integer part L times alpha is fractional part of L times alpha, and K times alpha minus integer part of K times alpha means fraction part of alpha, but minus 1 times fraction part alpha, and the absolute value of the fraction part. Okay, we take L is greater than K, so this is positive, and we calculate it. This number is smaller than 1 over n because this is the length of the interval. So alpha minus the integer part of if we divide L minus K this side, we get alpha minus integer part of L alpha minus integer part of K alpha over L minus K. This is positive integer, so the absolute value of this is 1 over n times L minus K. If we choose, the right, if we choose L alpha minus K alpha P and L minus K as Q, then we obtain L minus P over Q smaller than 1 over Qn. So this is the result. An example. Take alpha is square root of 23 and n is 5. Then the length of the interval is 1 over 5. This is equal 0.2. Calculate these 6 numbers. The first 5 lies on different intervals. By the pigeonhole principle, the last one must lie one of them lie same in the one of the same interval with one of them. In this case, 1 and 6, the first and 6th lies in the same interval, and our P, in this case, P is the integer part of 28 and the minus integer part of 4. This means 24, and the integer part of the not the integer part, sixth number minus first, is 1, and the absolute value of this minus this is this, and this is smaller than this number and this number. 1 over Qn. This is smaller 1 over Q. In this case, Q and N is equal. So the useless theorem is satisfied, and we know from the preceding observation the order of the denominator. When the order of the denominator is 1, this is also holds, but this is much general. Let us generalize. For a given alpha, we can look at for which t we can have an approximation with this inequality holds. We can say a real number alpha can be approximated to order t if there is a constant and this inequality holds. T can be any real number, any positive real number, of course, as far as I know. But the purpose of this presentation, we will focus on the case t is a non-zero natural number, and we will also take q to be non-negative and non-zero. We can do this. Yılmaz theorem said there exists at least one, because we construct at least one rational that satisfies this inequality. A question: does the Yılmaz theorem says all real numbers can be approximated to order 2? This means can we find infinitely many such rationals? A hint, of course. If alpha, in this case x, if x is an integer, what rationals satisfy the inequality? How many rationals? we can calculate if you want to try. You want to try? Maybe I can try. X minus x minus p over q smaller than 1 over q. This means that it's smaller p over q plus 1 over q. X p over q minus 1 over q kare. This means that q minus 1 is smaller than x, smaller than q plus 1. By x, and we obtain minus 1, minus minus p. And in this case, q, x, and p is integer. So this multiplication is integer. So the result is just can be 0. And we suppose q is positive and it can't be 0. So this number is 0. Then x is equal or q. This means that if alpha is an integer, it can be approximated with just itself. But of course, in this case, this can be p or q times over here, and here is any real number, but all of them is equal. Then we have a proposition. If alpha is a real number, if alpha is a rational number, there is the inequality is satisfied for only finitely. For no rational number, it can be approximated to order 2. But alpha is a irrational number, then it can be approximated to order 2. This is a distinguishing feature between rationals and irrationals, but there is more. We can differentiate a real number alpha if rational or irrational. Just look if can be approximated to order 2 or not. Reminder for an algebraic number of degree d. Let alpha is a real number, of course. Alpha is called an algebraic number of degree d if alpha is a root of a polynomial of degree d, and alpha is not a root of a polynomial of degree less than d. And this theorem of Liouville says if alpha is a real is an irrational number and algebraic of degree d, then we can find that such this inequality holds. The direct corollary of this theorem says an algebraic number of degree d can be approximated to order. It must be because we write C or Q. And if you write here, suppose alpha is approximated to order 2 d plus epsilon, then this means q to the puissance of q to the order of epsilon is smaller than c of alpha over c. Then this is an upper bound for q. Then there is no infinitely rational number. Right. Yes. Every irrational number can be approximated or at least 2. We know this from this fact, from this proposition 2. And now we know every algebraic number of degree d can be approximated to order. It must be. But this upper bound is tight. Can we lower this upper bound? Answer is yes. The preceding theorem was given by Lewin, 1844. Our upper bound is D. After long years, Axel 2 gave the lower upper bound to D over 2 plus 1, and Ziegler lowered upper bound to square root of D, and these two upper bounds depending on the algebraic number of degree of algebraic number. After some, Freeman Dyson lowered the upper bound square root of 2D, and finally Crossroads lowered the upper bound to 2. Our if an algebraic number of degree D can be approximated to order D, now our upper bound is 2 and our lower bound is 2. This means that every algebraic number can be approximated to order 2. And a reminder for transcendental numbers: if a real number alpha is not an algebraic number, then it's a transcendental number. This means that if any real number can be approximated greater than 2, to order greater than 2, then this number is a transcendental number. And this was the Lewin constructed the first concrete transcendental number system with this information. If a real number can be approximated to any natural number, then this number is transcendental. Now we can't improve the order 2. What about the bound 1 as a denominator? How about the constants? For a given alpha, consider the possible L such that the inequality holds. The same inequality as in the definition of approximated to order 2, but there is a constant L. Given an alpha, a real number alpha, the overall L that satisfies the equation is called the Lagrange number. Supremum of overall L that satisfies this inequality. And the set of Lagrange number is called Lagrange spectrum. If there is no such solution, by convention, we suppose L of alpha is 0. Now we know that L of any rational number is 0. Also, we have some examples. The Lagrange number of golden ratio 1 plus square root 5 over 2 is square root 5 square root of 5. The Lagrange number of this number, limit of L numbers, is square root of 8. This is the question: how can we calculate the Lagrange number for a given alpha? If we can find a sequence that converges to alpha and satisfies this equation, then maybe we can calculate. If we know L alpha, can we find a sequence Pi or Qi converging to alpha that satisfies the inequality? Another topic is continuity fraction. Given a real number alpha, we can express it as follows. This representation can be obtained by dividing every steps of division algorithm by a dividend. If you consider the division algorithm and divide every steps, then you will obtain this. It's called a continuity fraction representation for alpha, and is denoted A0, A1, A2. Actually, we can use this to get a rational sequence converging to alpha. This expression is fine if and only if alpha is a rational number. And an interesting fact, this expression is infinite if and only if alpha is an irrational. Let's take an example. Fibonacci sequence. we get the sequence, the relations of consecutive terms approach the fraction is equal to 5 plus 1 over 2, sorry, called the golden ratio. And we have this recursion expression, recursion formula. Let's write Fn over Fn minus 1. This is equal this equation, and this is 1. This is Fn minus 2 over Fn minus 1. Flip over this fraction, we get this. So, same representation nearly. So, if we use recursion, we get this complete fraction for the golden ratio. And everyone realized from the textbook the golden ratio can be calculated with complete fraction give a good approximation in general. Then moreover, Lagrange said if Pn or Qn is the sequence of the continuous fraction, and if the Lagrange number of alpha is greater or equal at least than 2, then this good approximation must be there in the sequence of continuous fraction. Also, theorem of Diophantine says there are infinite mean rations for every irrational number, such that the inequality holds. This means that every Lagrange number of irrationals is smaller, is greater or equal than equal to 5. This means that the continued fraction of alpha is its best yes. It's best approximation sequence. Reminder for Lagrange number of alpha, the set of Lagrange number is called Lagrange spectrum. We can calculate the element spectrum via continued fractions, but this is really this is just work for the continued fraction line periodic at purely periodic. We can calculate with these numbers, but not a straightforward process if other person Markov equation everyone knows from the preceding presentation. We can calculate Markov numbers with ease and construct a Markov tree. Markov's greatest theorem says the Lagrange spectrum below tree is given by this formula. Calculating Markov numbers is very easy, and this is a straightforward process. So the good part of Markov number is we can calculate the Lagrange number of alpha with ease easily. Let's calculate some of them, and this is the straightforward process, and this is the end. Thanks for the.
Thank you for the great presentation.